All right, let's look at some of the problems where we apply the concepts of work and energy. So, at a playground, the 19 kg child plays on a slide that drops through a height of 2.3 meters. So, let me draw this situation. If that's my slide, that's my height, which is 2.3 meters. The child starts at the top of the slide. The child is at rest. So this is my V initial, and that's equal to 0. On the way down, the slide does a non-conservative work of negative 361 joules on the child, right? So before we do anything, let's find the initial energy this particular child has. We know the energy is equal to delta U plus delta K. So that's potential energy and kinetic energy. So that would be mgh initial plus half m v initial squared. Let me consider this my 0 and this 2.3 meters, right? So I set my height as 0 at this point. So the initial height will be 2.3. So that would make this 19 kg child times 9.81 is gravitational acceleration, and the height is 2.3. Half times 19 times initial velocity is 0 squared. So this complete thing becomes 0, and my potential energy at this point is, let me just calculate that quickly, 428.7 joules, and that's my initial energy. Let's look at my final energy. Final energy is, again, delta U plus delta K. So mgh final plus half mv final squared is equal to 19 times 9.81 times. So now my final height is 0. So 0 times mv final squared. We don't know the final velocity, right? So this becomes 0 times half times 19 times vf squared is equal to should be 9.5. Yep, 9.5 vf squared is my final energy. So now let's look at non-conservative work. This should be equal to my final energy minus my initial energy. I know the non-conservative work is negative 361 is equal to 9.5 vf squared minus, so that's my EF, and that's my EI. Minus EI is 428.7. So technically this will be 428.7 is equal to 9.5 vf squared Vf squared is equal to, just quickly calculate that, minus 361, 67.7 divided by 9.5. 9.5 is 7.126. So Vf is 0.66 or 2.67 meters per second. Let me look at my so significant figures used is 2, 2, and 3. So I think I should just go with 2. That's my answer. Next question. So a plane tows a glider. If this is my glider and that's my airplane, it's mg. We are told that this is at an angle, right? The plane does a work of 2.00 times 10 raised to 5 joules. It moves at a distance of 145 meters, and the tension in the tow rope is 2560 newtons. So now what is the force in the x direction? The force in the x direction is T times cosine theta. So if T is at an angle theta, this should be cosine theta, right? Times x. Oh, that comes later on. So my W is equal to F in the x direction times x. So that's T cosine theta times x. Now I'll just substitute the values. 2560 times cosine theta times 145. So can I find the value of cosine theta here? So 2 into 10 raised to 5 divided by 2560 divided by 145. So 0.54, and cosine, taking an inverse cosine on both sides, theta is equal to 57.4 degrees. Right, that's my answer. What is the angle between the tow rope and the horizontal? Yep. All right, let's look at the next question. So we are given, at time 1, we are given the mass of the object and the speed of the object. So the first question asks me about the kinetic energy. So kinetic energy at time point 1 is mass times velocity at time point 1 squared. Right, so half m is 0.55 times 6.5 squared. 0.55 multiplied by 0.5 multiplied by 6.5 squared. The value I get is 0.6, which is equivalent to 12 joules. Alright, second part. What is the speed of the object at time t is equal to 2? So at t is equal to 2 seconds, we just know the kinetic energy. So again, writing the expression, right? So here we know Ke2 is 38. half times 0.55, we don't know velocity 2. So solving this, multiply 38 by 2, multiply 2 on both sides, and divide 0.55 on both sides. This should be equal to 38. Let's do divide by 0.55. 138.18. Taking a square root of this and this, V2 is equal to square root of 138.18, which is equal to 11.7 or 12 meters per second. Right? So how much work was done on the object between time 1 second and 2 seconds? Work done is equal to KE final minus KE initial. So KE final is KE2 and KE initial is KE1. This is just equal to KE2 is equal to 38 minus KE1 is equal to 12, which should give me 26 joules. Perfect. Next question. So here we are given two springs. They have a force constant, they have a force constant K1 and K2, and they are connected in parallel, which means both their ends, one of their ends is connected to the ceiling and one of their ends is connected to the plank. This is called a parallel connection. Let me make that a little bit clearer to see. This is both parallel connection. All right. How much work is required to stretch this system a distance x from the equilibrium position? All right, let's look at it. Let me first write this work done. If I am the person applying the work, I have to do the opposite of this work. So I have to perform half kx square work to stretch one spring, right? So if both of these springs, this entire system is stretched by distance x, should my work total just be equal to work done on spring 1 plus work done on spring 2? Yes, it should. So work done on spring 1 is half k1 times x square, and work done on spring 2 is half k2 times x square, right? Let me just collect the terms that are common between them. It's k1 plus k2. If I write it again but change the place this is in, is this equivalent to stretching a spring that has k total of k1 plus k2? Yes, it is. So instead of needing a spring that's like very, very stiff, I used two different springs. So this is why the parallel configuration of spring, it's useful. You can add multiple springs here and make it act like one spring that is very, very stiff. All right, let's look at the next problem. Here we are given a water slide that ends at a height 1.5 meter above the pool. If the person starts from, so this particular height is 1.5 meters. If the person starts from rest, which means VA is equal to 0 at point A and lands in the water at point B, what is the height h of the water slide? Right? Assume this is frictionless, so work done by non-conservative forces is 0. So that means my E final is equal to my E initial, right? Perfect. So let's look at a couple ways to solve this. I think there are a couple ways to solve it. Let me approach it the way I would solve it right now. So firstly, I need to find out the velocity at this point. The velocity here will be the same as my velocity at this point, right? So VBX is equal to, I don't know the value. Let me call this O. So VOX is equal to, again, I don't know the value. But one thing I definitely know is VBX is equal to VOX. It becomes a projectile motion problem from O to B. Right? All right, let's see how to solve this. So let's look at my E energy at A. Again, summation of my potential and my kinetic energies. I'm not given the mass, so let me just keep it as h. This is 0. That's my height equal to 0. So at this point it's h plus 1.5 plus half mva squared mgh plus 1.5 plus 0. So I'll just erase the 0. Perfect. Now at EO, the energy is again kinetic potential plus kinetic energy. Mg 1.5 because it's 1.5 meters high plus half m VOX squared. Now I can assume safely that there's no velocity in the y direction because it looks horizontal, and that's I'm trusting the figure at this point. I don't know the value of VOX. All right, so now let's look at the energy at point B. Again, mg, the height is 0 now, so that's gone. mvbx squared plus, there is definitely a vby in this case, and that's also unknown. All right, that's fine. We'll just leave it as vby. So the total energy here is vbx squared plus vby squared. These are my energies. So if you look at this expression, if you look at this, there are a lot of unknowns. Let me mark all my unknowns with red, right? So that's my unknown, that's an unknown. Mass, again, is an unknown. Vox is an unknown. Mass is an unknown. Mass is an unknown. Vbx is an unknown. Vby is an unknown. So there are multiple ways I can approach trying to find the velocities. One thing I can do is, I know first I'll try to find the velocity in the x direction. So I know this person went a distance of 2.5 meters, right? So I will apply my I know they went a distance of 2.5 and they fell a distance of 1.5. So first things first, I'll need to find the time between O and B. So the y distance they fell, consider all right, this is y naught plus vy voy dob plus half negative g dob squared. All right, what is the y-axis distance of B? It's 0. Y-axis distance of O is 1.5, 0. VOY is 0. And then you get negative g by 2 TOB squared. So solving for TOB squared, so TOB squared is equal to 2 times 1.5 divided by 9.81, that's my G, equal to 3 divided by 9.81, and then if you square root both of these, your TOB should be 0.55 seconds. So once you have your T, let me apply the same thing again. So x, but in the x direction, xp is equal to xo plus vox times tob plus half a is 0 in the x direction, tob squared. So xp is, if I consider this my 0, so I'm considering this particular x as 0 and this is 2.5. So xb is 2.5, xo is 0, plus vox is unknown. Our tob is, I found it as 0.55 plus 0. So I can find vox here. It's just 2.5 divided by 0.55. So that is 4.55 meters per second. Perfect. So now I don't need, I know the value of Vox. So looking at EA equal to EO, because there's no non-conservative work done. Let's look at my mgh plus 1.5 is equal to mg 1.5 plus half m Vox squared. I won't put the values in right away, but what I will do is I'll split this up into mgh multiplied by 1.5 right. mgh multiplied by 1.5 is common on both sides, so it gets cancelled. So you end up with mgh half mv not squared. Now m is common on both the sides, so if you divide by m, it just cancels out, and what you're left with is Vox squared is equal to 2gh. Perfect. Now we know the value of actually, let me not do that. By 2. If you divide by g on both sides, you get that. And Vox is 4.55 squared divided by 2 divided by 9.81. So h is 1.06. Let me look at the significant figures. It's 3 here, it's 3 here, so I'll just leave it at 3. And that's my answer. And that's the end of this video.